Hello everyone and welcome to Lab 9. This week we're going to be talking about predator-prey problems. And before we start, we're going to have a little bit of a discussion here, talking about the basis behind this problem. So, we have a marine biologist, Dr. D'Ancona, who is studying the population of species of fish. And he noticed that around World War I, he finds that the population or the percentage of total catch of cetaceans, which include sharks and skates and rays and all those types of fish, sort of had this pattern. Now, D'Ancona obviously was very puzzled by this, right? So obviously he would think that, oh, maybe this was due to decreased fishing during World War I. But this doesn't really explain the increase in percentage, right? It might make sense that the absolute population of like cetaceans was increased, but why the percentage, right? Because of the reduced fishing, we should also have a reduced population of food fish. So he's very puzzled by this, and he eventually turns to the mathematician Volterra. Now, Volterra, what he does is models this as a predator-prey relationship, right? So we have predators, which would be the cetaceans, and the prey, which would be the food fish. Now, he models it in a way which I'm not going to go into, but you can read the explanation here. But all you need to know is that we end up with this system of equations here. Alright, so we're going to start off by examining our particular solution or a particular set of systems of equations with these values substituted in. Now, question 1 asks to find the equilibrium points for this system, and these are the points obtained by setting x prime is equal to y prime is equal to 0. Now, this should be pretty easy to do. All we have to do is to set x prime, which is defined as x times 1.05 y is equal to 0. And we can see here that either x has to be 0 or y is equal to 2. Now we also have a second equation, y prime is equal to y times negative 0.75 plus 0.25x. And we also set this to 0. Now when x equals 0, then we have that y times negative 0.75 is equal to 0. And this means that y is 0. So this means that one of our equilibrium points here would be 0, 0. Now when y equals 2, we see that, well, 2 times negative 0.75 plus 0.25x is equal to 0, which means that x would be equal to 3. And we see that our second equilibrium point would be 3, 2. Now, question 2 asks us to take this equation and put it into p-plane. So, I have p-plane up right here, and let's open up, put in this equation, x times 1 minus 0.5y, and y prime is equal to y times negative 0.75 plus 0.25 times x. Now choose your scale so that the origin is the center of the picture, and the other equilibrium point is centered in the first quadrant. Okay, so we can do that. Let's set our minimum x to be negative 6, our maximum x to be 6, our minimum y to be negative 4, and our maximum y to be 4. So let's graph it. Now, let's plot a few of these curves in each of these quadrants. Okay, so we should notice that all the curves in the first quadrant here are, closed. You can see that in the p-plane messages that popped up in the upper left corner that a possible closed orbit was detected. Now, this is due to a general theorem which says that for any nice autonomous system, any closed orbit must contain an equilibrium point. So, what is the significance for the populations of food fish and cetaceans of the fact that the orbits are closed loops? Well, this means that for any initial condition, any population of possible population of food fish and cetaceans will lie on this curve. And any sort of impact, right? If it moves along the curve, that's all that matters, right? It's periodic. Now, for number 3, we have the p-plane plot gives a plot of y against x, and explain why, as a function of x, our original system yields this differential equation. And now again, this isn't too bad. All we have to do is to take these and find dy dx. So we realize that dy dx is essentially the same thing as dy dt over dx dt, which means that this equals y times negative 0.75 plus 0.25x over x times 1 minus 0.5y. So we're going to take this and put it into D field now. So use D field to plot some solutions to this equation for various initial data. Use the same ranges on x and y as part 2. So again, we can just put this in. We have y prime here with independent variable x. Y prime is equal to y times negative 0.75 plus 0.25x divided by x and divided by 1 minus 0.5y. And we're going to use the same ranges, so we have negative 6x, positive 6x, negative 4, positive 4. And let's graph it. And again, you should see that the curves are mostly the same. You might have to press stop a few times because they get stuck at y equals 2. So after plotting a few curves, you see that all the curves stop at y equals 2. So why would that be? Well, it's pretty obvious actually when you look at the equation. The denominator here says that y cannot equal 2. So this means that the derivative is undefined at that point. And so any point where y equals 2, this D field can't graph because, of course, the differential equation is actually undefined at that point. Now, for number 4, we note that the equation in part 3 is a separable equation. So this differential equation is a separable equation. So we solve it to show the general solution. And of course, we could do that here. So this is a separable differential equation, which means that we put all the y's on one side and all the x's on the other. So we transform this into the integral 1 minus 0.5y over y dy, and this is done by just moving it all over, is equal to the integral of negative 0.75 plus 0.25x over x dx. Now we can rewrite this a little bit differently as 1 over y minus 0.5 dy is equal to negative 0.75 over x plus 0.25 dx. Now, if we just take the integral of both sides, this shouldn't be too bad. We get natural log y minus 0.5y is equal to negative 0.75 natural log x plus 0.25x plus c. And taking the exponential of both sides, so e to this, we get y over e to the 0.5y is equal to c, so this would be a different c than our original c, x to the negative 0.75 times e to the 0.25x. And finally, by dividing both sides by this x to the negative 0.75 e to the 0.25x, we get that c is equal to y times x to the 0.75 over e to the 0.5y times e to the 0.25x. And this would be our proof for question 4. Alright, so question 5 has 3 parts, and we're going to assume that our constant c is going to be equal to 1/2. So if we have c is equal to 1/2, we can rearrange our equation from question 4 to look a little bit more like this. Now, when x equals 1, the left side here, this little bit over here, should equal approximately 0.642. And you can find the corresponding values of y, right? So when x equals 1, y equals what? Well, we can use this by just plotting on MATLAB and doing a little bit of estimation. So just a reminder that if you don't have MATLAB on your computer at home, you can always go to goremote.itap.purdue.edu and log in, and you can access MATLAB right into your browser. So here's going to be the code for question 5 here. We're going to have grid on, hold on. This will keep the grid on the graph and keep any plots we graph on the graph as well. Sims y turns y into a symbol, which allows us to graph it directly like this. And again, we have x equals 1 and z set equal to the left-hand side of the equation. You can see that this is the exact same as the lab handout, and we're going to plot the left-hand side of the equation as well. So what happens if we run this? Okay. So here we see that yes, z, our left-hand side of the equation, does indeed equal 0.642, like the lab handout says. And z is actually represented by y here, and y is represented by x. That's just the way that the graphs sort of play out, so keep that in mind. But we're looking for the intersection points, right? So we're looking for when the right-hand side of the equation, the blue graph right here, equals the left-hand side of the equation, which we have already established to be this red line, this constant, this 0.642. So we just look for the intersection point, like maybe right around here. And we find that our value of y, which makes this true, is 1.091. And similarly, on the other side, we have 2 solutions actually. We find that a second solution that makes this equality hold is y is approximately 3.27. Okay. So for part B, we want to find the values of y corresponding to 2, 3, 4, etc. And you will eventually find that there is no y value, so also approximate the largest value x naught of x for which there is a corresponding y. So again, we can just change our x here and run it, and we should get at least 2 different values of y, and we do. So here our new y, when x equals 2, y can either equal 0.679 or y can equal 4.364. So you will see that for some x, eventually you're going to have no solutions. So we want to find the maximum value of x for which this occurs, right? So we find that if x equals 8 turns out to have no solutions, let's reduce this maybe to x equals 7. Okay, we find that x equals 7 does actually have two solutions for y, maybe 7.5. 7.5, still not yet. 7.75, let's try. Oh, too high. How about maybe 7.6? 7.6, not quite. Let's try 7.65. Yeah, about here. So about 7.65, we see that we only have one solution for y. Now, why is this so, right? Question B also asks you why you typically get two such values. Well, remember, if we go back into B-plane, we can see that for some values of x here, we have two values of y, and maybe I don't have the exact value c equals 1/2 plotted here, but we can see that we do have a maximum here where there's only one y for any given x, and we also have a minimum x here for which there is no given y. But there is only one given y, and for the majority of x's between these 2 points, we see that there are actually two values of y which satisfy the differential equations. Now question C is approximate the smallest value instead of x for which there is a corresponding y. So we already know that x equals 1 gives a solution, so why don't we try something like x equals 0.5. X equals 0.5. Obviously, there is no solution, so let's try increasing this a little bit to maybe x equals 0.75. Getting closer, maybe 0.77. And that seems close enough. So we see that at x equals 0.77, that would be the minimum value at which there is only one given solution for y. And now we know that they're bounded. These two, the solution, there's two values for y only when x is between 0.77 and 7.66, I believe. Okay, so for question 6, we're going to continue part 5 to show why all of the orbits are closed. So define the functions f of x and g of y as follows, and we can see that these should look pretty familiar. If you scroll up a little bit and go back to this equation, we see that f of x is like the reciprocal, almost the reciprocal of the right-hand side, or sorry, the left-hand side, and g of y is exactly the right-hand side. And we see that, yes, this does satisfy these f of x and g of y. They do satisfy this. G of y is equal to c over f of x. And we have a few questions down here to answer. So if the orbit begins at the point in the first quadrant, then c is greater than 0. Why? Well, if it's in the first quadrant, then x is positive, which means that f of x is positive, and if it's in the first quadrant, then y is positive, which means that g of y is positive. So positive, positive means that c is also positive. Now, using fplot, plot the graph of g of y over this range, and using your graph, explain why if there is a positive value of y is for which the above equation is valid, then there will be 2. So we actually already have this plotted out almost. We could just comment out this over here and get our graph. And you can see that for any for most any value of y for which this works, we also have a second value of y on the other side, right? So here, here, and there's only one value of y at the very top here where there's only one single value. So these values correspond to the top and bottom of the closed orbit, right? So this might be the bottom of the closed orbit here. This might be the top. And explain why the limit as x approaches infinity of f of x is equal to 0. Well, we can see here that the top is x to the 0.75, but the bottom is an exponential, right? And we know that exponentials grow a lot faster than any polynomial does. So as x approaches infinity, then f of x should approach 0. So this means that if x grows larger and larger and larger, then g of y, well, since f of x is going to be approaching 0, g of y will also be going larger and larger and larger, and if f of x equals 0, then g of y is undefined. So this means that if we have some really, really large x, this means then g of y will be undefined, and there will be no value for y. And similarly, if x is approaching 0, well, we see here that this on top will turn the entirety of f of x to 0, and we get the sort of a similar situation, right? As f of x approaches 0, g of y grows without bound and eventually goes undefined. So this means that if x is sufficiently large, then there are no values of y for which the above equation are true, and sort of the same as x approaches 0 as well. So this means that this orbit lies over a closed interval on the x-axis, right? So there's some minimum x and maximum x, and therefore each orbit has a top and bottom and lies over a closed interval. So this proves that all of our equations are closed. And again, going back to p-plane, you can obviously see that this is true. So for question 7, we're going to be going back to p-plane, and we're going to plot x and y as functions of t for several different initial conditions from the first quadrant. And you might recall that we did something similar in lab 7. So we go here and we go to graph and plot x versus t or y versus t, but we're actually going to plot both of them. So I'm just going to plot one for the outer one and one for the inner one. So for the inner one, well, yeah, you could see that this is indeed periodic, right? We have very nice periodic motion here, and the period seems to be around maybe like 15, 14 or so. I'm just making an estimate here. But for the outer graph, well, we see that, okay, it's still periodic, but the period seems to have changed, right? It's closer to maybe like 10 now. So even though the graphs are periodic, the period does seem to depend on the initial condition. Okay, now let's try a numerical proof to prove that x of t and y of t are periodic. So if we let t be the period, we can compute the average values of x of t and y of t by these formulas, right? This is just the average integral, and this is the average integral for x of t and y of t. Now, we can actually evaluate these without knowing the period, or even knowing x of t. So what we can do is use our original equation, right? If you recall from the top here, y prime is equal to y times negative 0.75 plus 0.25x. And by dividing both sides by y, we get this equation. Then we take the average of both sides, right? We have 1 over t, where t is a period, and evaluate these integrals. This eventually turns out to mean that, oh, this side is 0, so 0 is equal to negative 0.75 plus 0.25 times the average of x. Now remember, we just moved this, we know that this would be the average of x, and so the average of x is equal to 3. Now we can apply a similar argument to find the average of y. So if we go over here, we have here that x prime is equal to x times 1 minus 0.5y. So if we divide both sides by x, we get that x prime over x is equal to 1 minus 0.5y. And taking the integral of both sides, like in the demo, we get 1 over t, integral from 0 to t of x prime of t over x of t dt is equal to 1 over t, integral from 0 to t of 1 minus 0.5 times y of t dt. Now again, realize that this right-hand side should equal 1 minus 1 over t times, or of the integral of from 0 to t of 0.5 times y of t. Right, because we know that the integral of 1 from 0 to t is just t over t is equal to 1, right? And if we evaluate the integral on the left side, we see that this should be equal to 1 over t natural log x of t minus natural log x of 0. And since we know that t is a period, these two have to equal each other, so this turns into 0. So we get that 0 is equal to 1 minus 0.5 of the average of y. And we find that the average of y would be equal to 2. Very interesting, right? We see that, remember back in the demo that we saw that the average of x was 3. So the average turns out to actually be the equilibrium point, the other equilibrium point that we found over here. Okay, so for question 9, we're going to look a little bit on the effects of fishing on the population, right? So here we have some alpha, which represents a percentage of the fish that fishing fishes up. That's a tongue twister. Now, a is some small constant. We're going to set alpha to 0.05. So we can go back to p-plane and plot the system. Minus 0.05x minus 0.05y. And if we take a look, in the first quadrant, they still do seem to be closed orbits. Now, how does this actually affect, the averages, though? So if we do something similar, like we did before, right? So instead, now we have let's start with x, wrong color. X prime over x is equal to 1 minus 0.5y, but we also have fishing, right? So we also have this 0.05 constant over here. And well, doing these same steps again, we can just sort of see how it plays out. But we can see that we get 0 is equal to 1 minus 0.5 y average minus 0.05, right? Again, I'm not doing all the steps. You should be able to do the exact same thing. But we see that it's 0.95 minus 0.5 y average is equal to 0, which means that the average of y is equal to 1.9 now instead of 2. We originally got it 2 here, but now it's 1.9. And similarly, for the x average, y prime over y is equal to negative 0.75 plus 0.25 x minus 0.05, 0.05. Well, again, we see that 0 is equal to negative 0.75 plus 0.25 x average minus 0.05. This means that 0 is equal to negative 0.8 plus 0.25 x average, and x average is now 3.2. So even though they're still closed orbits, our averages, right, our equilibrium points sort of changed because of the presence of fishing. So if you go back to like the original start, we can see that x represents prey and y represents predator, right? So when fishing happens, prey goes up, on average goes up, and predator goes down. And therefore, when there's a decrease in fishing, like Dakona figured out at the start of like our starting intro, when fishing is decreased, then we should see that our prey, our food fish, go down, but the population of predators, our cetaceans, goes up, which is exactly what we found according to this data, right? So if we look at our data up here, when there's a decrease in fishing, the percentage of cetaceans increased. And our mathematical model is now able to prove this. And that should be it for Lab 9. If you have any questions, don't hesitate to email me or post on a discussion board on Blackboard. You might get an answer quicker that way. And reminder that it's going to be turned in at the same time, 3:30 Eastern Time, next Tuesday. And I'll see you then.